Hi, welcome to this YouTube channel on EBSD. This is Professor Dingley's channel. Professor Dingley is a professor in material science from the University of Bristol, but now retired. But he continues to develop EBSD and is currently a consultant to BLG Vantage. Welcome, David.
Good morning to you.
Good morning, afternoon. It doesn't matter. People are watching at any time of the day.
Okay.
So this chat, we're going to be exploring EBSD, and this particular episode, we're going to just be looking at how you are involved in EBSD, your story, where it began for you and how it developed. And then in later episodes, you're going to be diving more deeply into different areas of EBSD, but not just the basics. We're going to be going really deep into the kind of cutting edge. So let's hear a little bit about your story.
Well, I was a reader at Bristol University, and my area of research was crystal interfaces. That followed on from earlier studies on superplasticity, where we observed that the deformation mechanism there was 100% grain boundary sliding. So I had this interest in grain boundaries and why some boundaries behaved quite differently from others. For example, let's just take copper. We know copper is a very ductile material, but if you add just one part in a million of bismuth to the copper, it suddenly changes from a ductile to a brittle material, and what's more, the failure mechanism is at the grain boundaries. So that's a curiosity. Obviously, it's due to segregation at the boundary, but some mechanism going on in the boundary, and that would be due to the structure of the boundary. So that's where I was started from.
Even though you have one part in a million, it had a huge effect on the whole material.
Oh, it is quite dramatic. It's a classic example. But segregation to boundaries does do things like that. And there is a big area of exploration. And that's the area I was working on, and I had a very, very good student, Bob Pond, who then became professor of material science at Liverpool University. And he used the transmission electron microscope to investigate.
Sorry, what years, where are we talking about? The 1970s?
We're talking early 1970s, we're talking with Bob Pond. And he was looking at using the transmission microscope to investigate the boundaries. And he got some wonderful pictures of dislocations trapped in the boundaries. But he could see that there were additional boundaries, which we named grain boundary dislocations. They could only exist there. And he investigated the Burgers vectors of these things. And later on, with Andrew Bezic, we investigated the mobility of these type of dislocations in boundaries. So that's where it was. But Professor Pond's work showed that extended over 3 to 4 years, but he only investigated 12 boundaries during that whole time. A completely inadequate sample to discover fundamental mechanisms. And it was decided we had to have a better method of obtaining the crystallography surrounding grain boundaries and to observe the properties that went with different types of adjacent boundary orientation relationships. At that time, scanning electron microscopy was an emerging science. There were very few microscopes available. At Bristol we had one, fortunately, and there was others at Oxford and Cambridge, and it was Sussex universities. And just small groups of us were investigating ways of doing electron diffraction in the scanning microscope to get the crystallographic information out. The group at Oxford were working on what's known as selected area channeling patterns. I was in fact working on an X-ray technique, but was generated by the electron beam in the microscope. That was called Kossel X-ray diffraction, and Professor John Venables at Sussex University, he was working on a technique which he called electron backscatter diffraction. And all those things were going on in the 70s. I saw John Venables give a paper at Newcastle University in the early 70s, where I saw his technique. I thought it's an excellent looking technique. It's very similar to Kossel X-ray diffraction. So I went back to my lab and I tried to reproduce it, but I couldn't reproduce John's results because I had the wrong sort of phosphor in the microscope. It just wasn't responding. So I didn't get anywhere for a few years on that technique. But by the end of the 70s, in 1979, I was asked to compare all three techniques. And I said, yes, I'd do that, and present a paper at the electron microscopy meeting in Chicago. And so I decided to use the same specimen and use all three techniques to compare their results. But this meant I had to get the Venables EBSD technique working, which I did when I replaced the phosphor screen, which I hadn't been successful with a photographic film. And then remarkably, there was this pattern. It came out so simply. The student who actually took the picture was Nezam Razavizadeh. And here we saw this EBSD pattern. It was on film and therefore very high resolution, very much higher than what one could, and John Venables was obtaining using the 35mm film photographing a phosphor screen through a lead glass window. This picture was so remarkably good and I could analyze it. And I concluded in that paper I presented at Chicago that electron backscatter diffraction was the technique to use. And in the 80s, I started taking John's method and developing it and making it automated. That is, that we could tie a computer to superimpose graphics over the EBSD pattern and thereby automate the determination of crystal orientations.
Previously to that, then, it was on film. You were developing film in a dark room, and that's where you thought, well, you need to automate this with a camera.
That's exactly right. That's how it was. I was very fortunate to meet people working in low light level television cameras, silicon intensified target cameras, and that was Tony Moon and Roger Harris, quite near to Bristol. They were developing cameras for the nuclear industry. And I met them by chance. I told them I saw what they were doing, and I said, if I could have one of those cameras, I could see these EBSD patterns live. And with the knowledge I already had of how to index them, it was easy steps to develop software so that they could be identified online. I could measure an orientation in about 3 or 4 seconds at that point. It was a certain amount of manual input as well. But that was the start. And it moved on to what people now know as EBSD after a meeting at Los Alamos. It was a texture meeting, in fact, at Los Alamos. And I met Professor Brent Adams, who saw my talk and said, well, if you could do that, that would be a tremendous boost to the texture research community. Could he have a copy of the system? Which at that point, Oxford Instruments were interested in commercializing it. And I said, well, I'll put you in touch with Oxford Instruments. They'll provide the hardware through Tony Moon, and I will provide the software and tutor you in how to obtain the patterns, etc. Brent Adams did that. It was very successful. He moved to Yale University. There's only a handful of people doing it at that time, just a handful. And he moved with his research students. They were, in fact, Stuart Wright and David Field, well-known names in the community now. And there we developed a fully automated method, so by you just press one button on the computer and it captures the images, image processes it, and indexes it. And after that, which was funded by the National Science Foundation, Brent said, this is too important a technique to leave to commercial companies to develop. Why don't we develop it ourselves as a commercial instrument? And he said he would like it if I took the reins on that, and which I did, and we formed a company called TSL, and that started it to become well known in the community.
Nowadays, it's there are hundreds and hundreds of laboratories around the world with this system running.
That's true. It's in the thousands now. Yes.
The principle of being able to analyze materials at this level.
Absolutely. I mean, it combines electron microscopy, which gives you the topography of the sample, energy dispersive X-ray analysis, which gives you the chemical composition, but it extracts from the specimen the microstructural data. It adds to it the crystallographic nature, so you know the crystal phase rather than just the chemical composition. It tells you the relationships of the crystallography between neighboring grains, and therefore thereby produce that answer I wanted to set out to measure in the first place. What was the orientation relationship between grains which fractured at boundaries and those that didn't, those that slid easily at the interface and those that didn't? And that is still being investigated today, because there doesn't seem to be a simple set of rules. And it has become, the technique has had to collect vast amounts of data and in 3 dimensions. So this required technological advances by the microscope companies, which has come to fruition. And you can now serial section bulk samples and get 3-dimensional information regarding these grain boundaries, masses of it. It has to go fast because you want lots of data. So the camera companies have been coming up with enormously fast cameras, collecting images over 1,000 a second, maybe into the 2,000 a second. But that means the quality of the patterns has gone down, and therefore you need different methods of indexing the patterns that I developed early in those 1980s. These become cross-correlated pattern recognition, looking up thousands of stored images to find a match, and thereby finding the phase and orientation automatically that way. So the technology and the science behind it is enormously advanced, lots of people in the field. And that leads me to what I'm doing now, and that is going the other way. I still want to get accurate data, high angular accuracy, and that means has led us to determine the strain within the crystals. And it's the strain at grain boundaries that is rather a crucial interest. How you do that is going to be a subject of what I'm going to say in the future. It requires more careful microscopy and a much more intensive computer analysis, but it's successful. And the degree of success I'll be discussing, and how to interpret the data in later talks.
You really have made it the majority of your working life dedicated to this field. So, I mean, you're clearly an authority on the subject, and you won't let it go.
Well, maybe it won't let me go, because it's a great challenge, and it's stimulating to work with my colleagues now that I'm retired from the mainstream. I work with Graham Meaden, who was one of my students, and also with my son Damien Dingley. He does the software along with Graham, and I poke around with ideas of how to interpret the patterns.
You're not satisfied with staying in the main field of EBSD, but really still trying to push the limits of it to determine, like you said before, about these boundaries?
It's looking at aspects of the subject which weren't my speciality when I started. I was interested in the boundaries, structure of the boundaries. They're interested in the distribution of the orientations, because that's enormously important in determining the properties, whether they're mechanical properties, electrical properties, magnetic properties. And it extends through the fields of metallurgy, semiconductor physics, and geology. That's why it's such a wide field. And and as retired, not having access to laboratory facilities, I don't have a microscope anymore. Therefore, I have to do everything on the computer. Yes, let me just show the direction I've been going, and I'm hoping, and I suggest that other people take it up. I'm not alone in it. There are something like a few dozen people doing research at the academic level, and then others are using this new technique of measuring strain at high accuracy. So I can show you a couple of slides about that, okay? Here's just a few slides to illustrate aspects of EBSD that aren't in the mainstream. The first micrograph on the left, all those in the mainstream will recognize backscatter micrograph, or as it was originally called by Professor Brent Adams, orientation imaging micrograph. The grain structure of the material is shown clearly. For example, just pick out some features here. Metallographically, everybody will recognize it as a twin structure in this material, which is a steel. These will have special grain boundaries. They're the most common special grain boundaries that exist in crystalline materials. But what I want to show now is I take this detail in the micrograph and increase the magnification on the microscope so it fills the whole screen. And I said I'm interested in the grain boundaries, and we would like to know what the strain is at the grain boundary. So if we look at the next slide, so in this next slide, it shows it's an in situ experiment going on in the microscope. We have a tensometer, the work being done by TSL Laboratories in Japan, who build the tensometers. And here we are increasing the load on the sample. The axis of loading is horizontal in this case. And in this region, up to here where it's a straight line, this is the elastic region of the material, and here it starts to become plastic, whereas it goes over there. This is where dislocations are thought to start to be generated to enable the plasticity. This is the loading on the specimen, and here are just three snapshots of the information that one gets out of high resolution electron backscatter diffraction. We're looking at the strain in the sample, and that's being shown as a color now. We've superimposed the grain boundaries from standard EBSD. Now, the green here, it has a strain in it of 0. We're at the 0 load, and that's what you'd expect. But as we go up in the loading, the colors start to change, indicating a higher elastic strain in the material, until we get to this yield point, and there are distinctive zones of high strain with some straight lines in them here and here. We'll just look over here. You can see it better in the stress map here. These are the stresses residual in the specimen. These straight bands here, these are caused by dislocations zapping in across the grain. Now the next slide shows a detail of these. This strain here is the strain across the horizontal in that direction there. We can see detail of build-up of strain at the interface here and here, and in this particular grain here. But this has gone blue. That is showing it's in compression. That grain's gone into compression, even though the specimen overall is in tension. And we see little areas where the stress the strain is localized, very, very localized. These are the straight lines I mentioned before, are the slip lines. In here, we're looking at the defect structure, where the dislocations are. You see a high buildup of dislocations over here on this boundary. But it's not where the slip lines are on this side of the boundary. You see the strain is very little there, but it's large on this side. So that's a curiosity. That should make people think, why should that be? Right at the boundary, and that's only 50 microns. So we're looking at about 1/10 of a micron from the boundary. They're very high strain indeed. So something's happening in the grain boundaries. We know there'll be sources of dislocations later on. But that's the sort of detail one is looking for, and that's why you have to have a very specialized technique to extract this data, and that is what I'll be talking about in future talks. Those that are interested in recrystallization in materials will be interested in these local high concentrated, very small areas with high concentrations of stress, and that's where recrystallized nuclei will come from. They're not all on the grain boundaries. Some are inside, and one would have to investigate why they're there. So it's not only how you get the patterns, but how you interpret them and how not to be misled. So you want to try and put as much information together at the same as you can. And I'll just show you this. This is from the SEM image. This is an SEM standard scanning electron microscope image. And what is showing up, the microstructure is showing up. Here are the boundaries. We haven't overdrawn them here. That's how they appear in the microscope. And you see these are the slip traces, which are shown as strain in the other images. Those there are here. And these here are the strain here. So that's a topographical image. This is a strain image, and this is a dislocation density. It tells you how many dislocations in this zone. So you want to put these three bits of information together to try and understand what is actually going on. But you see, let me just point out a detail there. That's high strain. It's near this, it looks like an inclusion in here. So it might be caused by that. To start with in the talks, I'll be talking about the diffraction patterns that you get from each of the points. And by the way, the dots in the image people will recognize in scanning electron microscopy as being contamination marks where the beam rested while we collected the electron backscatter diffraction pattern. So you just get an idea of how many patterns were recorded just to get this image down here.
Okay, well, thank you, Professor Dingley, for the introduction and the background on where you have been developing this. Really looking forward to seeing the other episodes where you're going to be discussing in more detail. So thank you very much again. Do you have anything else to say before we leave?
No, just that I'm looking forward to it, and I'll start preparing the slides needed.
Okay, that's great. Okay, well, thank you.
Thank you. Bye then.
Next time. Bye.
Bye.